So in this video, we're going to define what's called optic sign. If you look up a mineral in a book, you might see something like this: orthorhombic with a positive sign, or maybe monoclinic and then a negative sign. So they're indicating the crystal system, but they're also indicating whether the mineral is positive or negative. So what do they mean by this? Well, there are two ways of defining it. The first one involves uniaxial minerals. And so for uniaxial minerals, remember we only have two values, two principal values for the index of refraction, an N epsilon and an N omega. Well, if it's the case that, we'll just draw omega and drop the N part. If omega happens to be greater than epsilon, then we say that the mineral is positive. So if omega is greater than epsilon, here we mean the index of refraction, so this guy here, that means that this is the slow ray. So remember, big N means slow velocity. If, on the other hand, it is epsilon that is greater than omega, then we would say that the mineral is negative. So that's how we decide positive and negative in uniaxial minerals. With biaxial minerals, it's a little bit different. So here we have the optic axes and the 2V angle that represent the angle between those optic axes. And then we have these crystallographic directions, X, Y, and Z. So for the case of biaxial positive, we are concerned about the B, the value for N sub beta. This is N sub alpha, and this is N sub gamma, and for the Y, this is N sub beta. So we're interested here in how N alpha compares to N beta. And if it is the case that beta is closer to alpha than it is to gamma, then we would say that the mineral is positive. And if it is the case that beta is closer to gamma, then we say that it is negative. So the beta value, is it closer to alpha, positive, closer to gamma, then we say that it's negative. There's another way of looking at it, though, and it is a way that's often illustrated in mineralogy textbooks and is shown here. Both these diagrams are from Dexter Perkins' online mineralogy textbook. This gray plane here that contains the X and Z axes is also noted as the optic plane. So the optic plane is the one that contains the X and Z optic axes. And keep in mind those do not necessarily correspond to crystallographic axes. Within that optic plane are the two optic axes as shown both here and here. This is effectively the same diagram. But we can also look at this. These two optic axes are defined by an acute angle, and that acute angle is 2V. But we can also have an obtuse angle, which represents the complement to that acute angle. If we're looking down the acute angle, we call it the BXA. And if we look down the direction of the obtuse angle, it's the BXO. These are directions that bisect these angles. So the BXO bisects the angle between the optic axes, and so does the BXA. Well, another way of defining positive and negative is looking at how that obtuse and acute angle are arranged. If the acute angle is shown here, let's say this happens to be the z-axis, where the acute angle is around the z-axis, then we would say that the mineral is positive. On the other hand, if this acute angle is around the x-optic axis, then we would say that the mineral is negative. So that's another way of thinking about positive and negative for a biaxial system. Which direction, x or z, bisects the acute 2V. So here we're not worried about the obtuse angle. We're only interested in looking down the BXA. And is that acute angle bisected by z? If it is, then the mineral is positive. And if that is around x, then the mineral is negative. So that's another way of defining positive and negative. So that's the theory behind it. In other videos, we'll take a look at how we can actually make these measurements using a petrographic microscope.